Hello everyone, I'm Chen. Today I will talk about my paper, LibDroid, a static analysis toolkit for Android native library. This work is supported by NIST and CSIF, incorporated with Chris under the supervision of my advisor, Dr. Yong Guan. Here is a roadmap of my talk. I will start with a brief introduction of some background knowledge, then move forward to the motivation with example. Afterwards, I will discuss the technical detail about the LibDroid framework, as well as how to make use of LibDroid, followed by evaluation section, and conclude with a short summary and discuss about future work. So Android library is structurally the same as the Android app. It can include everything needed to build the app, including source code, resource files, and Android manifest. However, instead of compiling into APK that's run on device, the Android library compiles into Android archive file that you can use as dependency for an Android app module. Native library, they are written in C and C++, and the native codes can interact with Java method through the Java native interface, where the native method can call Java method, create and update Java objects. To compile the C and C++ codes is require the native development kit from the Android SDK package, and use the CMake, which is an external build tool that you use to compile and build the native codes. Recent statistics shows over 40% of the regular Android app make use of native codes. So Java with the JVM optimized bytecodes can generate pretty fast code, but native codes can be faster and useful in areas such as gaming, physical simulation, and signal processing. Although you can do all of that in Java as well, using the JNI for low-level access, but let's still add a slight overhead. Because Java source code is compiled to bytecodes and stored in a jar or APK file, which are the zip files. So at runtime, the JVM loads the zip files bytecode and compile it into machine codes. So compare that with the native codes, which have no warm-up types. So native codes can have huge performance boost when executed on the Devil virtual machine. In addition, native codes have direct usage of system resource with the ability to manipulate its own process components. Meanwhile, Java codes, basically are bytecodes with a lot of information about what's the nature of the original source code. So object definition can easily be detectable, such as the object name, variable type and names, etc. But for the C and C++ codes, it compiled down to the machine languages, which is not required to have such information. So it will make them hard to reverse engineering. Most Android malware spotted is written in either C or C++ because it's black box feature that is easy to escape the traditional static analysis of malicious behavior. Android app usually use Java to implement the logic, and the Java interface provide developer with the ease of accessing multiple layers of abstraction. Native codes, by contrast, is implemented in a much lower level, while the Java can easily be decompiled, which just convert the binary back to the human readable source code. It is much harder to do this with native codes. So to make the malicious behavior harder to detect, more and more Android malware are written in native codes. Here is a motivating example which can demonstrate the challenge to retrieve data flow for Android native library. It's the code snippet of a real-world app. It consists of codes written in Java, which is activate components that loads a native library, face web Android, and imports a native method, main activities and data. And for the native library, it exports the native function, which leverage NDK library to read the Java objects. So take this application as an example. A sequence of events will be triggered. The main activity invokes a native method, main activities and data, where you pass with the URL as arguments. And the native method, main activities and data calls a native API to obtain the timestamp information, and the string variable receive the visitor URL and concatenate with the timestamp. And the native method, main activities and data receive the sensitive data, which contain the visitor URL and timestamp, and eventually write to file. So in order to retrieve the forensic artifacts generated by the native library, we need to create a process data flow summary for each native method. However, existing study make an over approximation for each argument and return value in the native method call. So they take the union of the 10 tag of all the input parameter and assign the union to the return value. So this approach overlook the native source and think. On the other hand, they also have the over-tainting problem, since it failed to disclose the true relationship between the input arguments and the return value. Here is an overview of the framework. So LibDroid loads the shared object file of each application and conduct a static binary analysis. The binary analysis parses the sequence of the GNI function calls in the body of each native function. And based on the pattern of the GNI function call sequence, we can find the Java API calls in native codes. And then LibDroid will check if the method call is a source of think API on the control flow graph, and leverage the taint analysis to retrieve the data flow of each native method. So the first phase of the LibDroid is the pre-processing phase. So giving an app, we first unpack the APK and modify the properties in build.gradle file to query the dynamic loading libraries. After obtaining the native library, we use Maxima to transfer the shared object files into RVM Analyzer, which can be converted and linked into machine-dependent assembly languages code. Second, we generate the method list and leverage the RVM Analyzer to build the control flow graph for each method and construct the entry points. However, our RVM Analyzer itself is unable to identify the data flow from the source to sink. It cannot identify the file path where the evidence is written to. We define a taint structure for each variable from the entry points in the control flow graph. We propagate variables taint tag by applying a forward data flow analysis. So the taint tag can be used to identify the type of evidence. At the meantime, we track where the evidence is written to by monitor the invocation of native file paths. So we propose a taint structure which contains two information, a taint set is corresponding to the type of evidence, and a path, which is the file path, where the variable which contain the sensitive information is written to. And the propagation rule define how tags are updated when applying and when analyzing each statement in the native libraries. Our rules apply to the arm and sum instruction of the shared object files. For the analyzing engine, the native source and think There are three kinds of source and think API in the native codes. The first one is the Linux system calls, and second one is GNI function that invoke Java methods. And third one is a native API, which can generate or store the sensitive information. We first combine the publicly available source and think in existing tools, including FlowDrive, SUSE, and DroidSafe. So we manually analyze all the native APIs available for the Android system and collect 47 native source API and 17 native sync API, where we define sync as system API that write data to file system or send out data through a socket. And source API is where sensitive information are created. And for the summary-based data flow tracer, SCT take the control flow graph of the native method as an input. Then we calculate the ingrid of each vertex in the control flow graph to verify whether a basic block does not have any successor that has not been analyzed. So in this way, each block needs to be analyzed only once. If there is a circle in the control flow graph, we will break the circle arbitrarily to calculate the ingrid of the basic block. And for each basic block in the block list, we apply the 10 propagation to update the 10 set of the corresponding register and generate the summary of the basic block. So the callee method summary will propagate to the caller method until the return is reached. When the data flow analysis of all block is over, we extract the 10 set together with the path related to the return nodes to build the summary of native method, which illustrate the relationship between the return value and arguments, as well as the invoked source and sync API within the method. When performing orthometric comparison with variables, we model the condition to a tree of operations as an abstract syntax tree. So the abstract syntax tree can later on be translated into constraints for a MST solver. So we leverage the SMT solver to compute the results of two ASTs. Our goal is to provide an efficient native library summary to avoid potential evidence being mishandled by app developer or existing analysis toolkit. We will build an Android evidence database for Android native libraries, including widely used open source native libraries, as well as the native library they collected from the real world popular apps. So in our static data flow analysis, we uncover the 10 propagation rules between the input parameter and the return value, define a customized 10 structure for local and global variables, and propagate the 10 through the forward analysis. So each record of the database represents the analyzed results of a native method, which present the 10 propagation logic between the return value and input parameter, as well as the type of identified data that the method is generated. In order to evaluate the performance of LibDroid, we first evaluate LibDroid with native flow bench, which consists of 22 benchmark apps. Then we evaluate the LibDroid using 52 open source Android native library, including several flagship imaging processing library. We conduct a performance measurements of our system in terms of accuracy of its SDT based on the benchmark app and the open source native library. Then we evaluate the LibDroid on the native library we retrieved from over 2,000 randomly select real-world application from the Google Play Store. So for the benchmark evaluation from the native flow bench, we evaluate the accuracy of LibDroid, compare it with JNSF and FlowDroid. We run each tool against the all the benchmark apps to check if the tool can correctly report the potential data leakage and corresponding data bus. Among the 22 benchmark apps, FlowDroid treats all native method calls as black box and apply a conservative model to tint all the other arguments if one argument is tinted. So it identifies one false positive pass at the native source clean and failed to detect most of the data paths among the 22 benchmark apps. While the JNSF reports 2 false positive, while the LibDroid only have 1 false alarm on the native complex data string up. So this is because LibDroid doesn't have a precise string analysis implement at this time. And for the open source evaluation, open source native library, they have collect 52 open source Android native library to measure the performance of LibDroid. To analyze these open source native library, they include source and thing collected from SUSE, as well as the native source and thing discovered from the Android native APIs. So developer and researcher can leverage the precise data flow analysis results as the 10 propagation rules for the native method. Among the 52 open source native library, we notice five of them invoke and generate sensor type of evidence. 45 of them will access and store time information to the file system. And 17 native libraries store users' text inputs, and 40 of them obtain VDC URL. In addition, we found many of the native library requires device ID, UUID, and context and mobile country codes, which are listed as other. We also randomly select over 2,600 real-world application from Google Play Store, where we unpack the APK file and obtain the native library. We use LibDroid to build the data flow summary for this Android native library. So for a large scale of analysis, we create an automated testing script where we set a 1 hour timeout for each Android native library. So this table summarizes our analysis result for each type of the identifier data we found from this Android native library. So a reported record contains at least one type of the identifier data, such as time, text inputs, sensor, or VDC URL. So we categorize a file path as a dynamic file path if the file path includes the pattern of timestamp, UUID, or Android versions. Otherwise, we treat it as a static file path. So as summary, we develop LibDroid to automatically identify forensic artifacts and construct information flow for Android native library. For future work, we will keep working on the native source and thing analysis and keep working on establish dictionary-like Android evidence database. We store the native library metadata with all the detected forensic artifacts. And we will continue work on develop a precise library matching mechanism for matching the target native library against our database for better usage of our results. Thank you for your time. If you have any question, you can reach me at the following email address. Thanks.